Hello, I am Mohammad Sadri, postdoctoral researcher at TU Kaiserslautern, Germany. This is video section 7 of section 3 of lesson 7 of the videos that I am creating for the ZYNQ device and designing embedded systems using ZYNQ. In previous two sections of this lesson, I briefly described what we want to do, and then we created, in fact, the building block of the module with AXI interfaces that we want. So we created the basic RTL example, and I just have the ports correct for the RTL example, not the internal code, but for now it is enough, and then later I will complete the RTL in the next video. So in this video I am going to use that module inside a kind of signal processing tool chain inside Vivado. And yeah, these videos, they are not official, they are hobby videos. I am creating them for myself. Of course, they are later used as a kind of reference for people whom I know and ask me questions regarding the ZYNQ device. I can refer them directly to these videos and use these videos at your own risk. You should always consult the official ZYNQ documentation for whatever you want to do. That is the main reference. And so let's continue. What I want to do in this video is, in fact, I want to use the Vivado environment and to create this chain. The chain begins from Sample Generator and then goes to the AXI asynchronous FIFO, FFT DMA, in fact AXI DMA, and then we go to the ZYNQ PS. We use the Vivado environment and we build this simple architecture using Vivado environment. So what I have up to this point, I have this folder that you are familiar with. This folder. So we have my course. It contains, in fact, the block, the custom block, the custom module that we have created, and our custom module. It has this set of these two AXI interfaces, and it has these signals, and then we have the SDK. The SDK folder is at the moment empty, and later when we want to develop a program for the ARM host that configures the DMA engine, in fact we will store the program inside the SDK folder. And then we have the TCL folder. It will keep our TCL files. So when I design the architecture inside Vivado, indeed I save equivalent commands of what I do inside Vivado as a TCL script. And then later, whenever we needed to recreate the architecture, we will use the TCL script. And the Vivado folder here is practically right now kind of empty. It doesn't contain, it just contains these simple files, and the Vivado environment here, it is ready for us to begin the project. So I go ahead, create new project, and just I press next. And for boards I use the ZC706, and the point is what I say here is general, is not necessarily for the Z706, and you can use it for whatever ZYNQ device that you have. So we have created the project, and in parallel what we are doing is we are generating also a set of TCL commands. So I keep a file. So I say vim run example.tcl, and this is the TCL script that I am creating, and I keep all of the commands inside, all of the commands that are issued inside Vivado in this file. So this is June 30, 2014 created. I usually like to keep a kind of track of the changes that I make to the file at the top of the file, and a small description. This is the TCL script which builds our example system. And for now we have create project, and we have indeed these two TCL commands, they are issued. And yeah, it's okay for now. And I continue create block design, and we create the block design. Again, another command, and the TCL console is generated. So yeah, Germany won the football. And so here, create block design, and here I will add my design. Okay, and the first thing that I will do, I want to include inside my block design the AXI Stream block that I have just created, the AXI Stream block that I created in video section 2 of this lesson. So what I should do, I should add the repository of that, in fact, IP core, that block that I have created. I should add that repository to this project. So I come to project settings, and then IP, and then add repository, and I come to the my codes folder. And then if you remember, the actual core is inside IC repo folder. So I just select IP repo folder and I add it here, and Vivado searches in the subfolders inside the location that you specify, and it has found Sample Generator V1. So I will apply and I will OK, and then here inside the block design, if I press Ctrl I would expect to see Sample Generator V1. Okay, this is our block. It is now added to the in fact block design of Vivado, and we have some set of new TCL commands. So I add these TCL commands to my file as well. Yeah, so update the repository of the project. These are the commands, and then add the sample generator to the block design. Okay, and for that one, the commands are the following. So okay, let's continue. This is the block, and what I want to do, usually it happens that in your design, the A to D, or the logic which is operating outside your ZYNQ device or outside your FPGA generally, it's running at a different clock frequency than your internal circuit inside the FPGA. For example, this is kind of connected to an A to D from outside through this port, and that guy is running at 50 megahertz, while the rest of the circuit that I want to insert here, they can run at 200 megahertz. So there should be a circuit to convert or to transfer from one clock domain to another. So suppose that I have FFT, I have the fast Fourier transform block, I have the fast Fourier transform block inside my design, and so I have these two guys, and I am planning to send the samples from this one to this one, but I want, and I know that this guy can run at 200 megahertz when I have the ZYNQ device. It can run at 200 megahertz, and for a specific workload, the faster this guy can run, the smaller will be the total area, right? Because it can use the same logic during several clock cycles to do the required operation. So if both of these guys, they are running at 50 megahertz, then at each clock cycle in 50 megahertz, a new sample will arrive at FFT. So the FFT module should implement a completely parallel or completely pipeline path so that it can accept one sample every clock cycle. While if I run this guy at, for example, 200 megahertz and this guy is running at 50, in front of each sample which is arriving, which is generated by this module, we have 4 clock cycles here. So the implementation of FFT module should not be so that it can accept every clock cycle a new sample. It needs to accept every 4 clock cycles a new sample. So the logic can be reused during these clock cycles. It can instantiate a single piece of logic and reuse this logic through these clock cycles. The result is a smaller circuit for the FFT module, and this is what usually the designers do. So if this clock here is going to be clocked at 200 and this clock here is going to be clocked at 50 megahertz, then we need a kind of conversion between this clock domain and this clock domain. What we do, we insert an AXI for data FIFO. Let's see if this guy is what we want. So I insert this block and let's make them. Okay, so what will happen is that I will come out of the sample generator, I will go to the data FIFO, I will come out of data FIFO, and I will go to the FFT block. Okay, so we have this architecture, and here for this design we are supposed to have 2 different clock domains. I will talk about this just a few minutes later. We have the FFT module. There are lots of points that I should say about these 2 guys. I will tell them, but for now let's make the chain complete. So after FFT module, I want to somehow store the results of FFT, the results of calculation, processing that I have done on the DRAM memory of the Xilinx ZYNQ device. As I told you in lesson 8, there is a DRAM controller at the PS, and usually you have connected some amount of DRAM to this DRAM controller, and the ARM hosts, they have also access to these DRAM controllers, and it's a very good idea to store the data on these DRAM controllers so that later the ARM hosts can have also access to the processed data and do their own additional task. So what I want to do is, first I have the ZYNQ PS, and this is the first time that I am instantiating a ZYNQ PS inside my design. So I type ZYNQ and I select ZYNQ 7 processing system, and this guy which is now added to my block design is the ZYNQ PS. By the way, I have forgotten to, in fact, to store a large number of TCL commands. So before I continue, let's first store the TCL commands. So up to which point I have here, add the sample generator to the block design. So here, this one I have, this one I have, this one I don't have. This is the command that is adding the FFT. So I add it here, add the FFT block to is enough, add the FFT block, and then some moves, not important. Regenerate block layout, not important. This is the data FIFO, add the AXI for stream data FIFO to the block design. So okay, regenerate, and then I have some connects. Usually I put connects at the end of the script when I have, in fact, instantiated all of the blocks that I need. So I copy these, and for now I create a complete separate section. I call it connections, and I put them here. And for now I add the rest of the guys here. So here I have the code with which I have added the ZYNQ PS. Okay, so I copy this and I come here, add the ZYNQ PS to the block design. I paste this guy here, and one of the lines is a kind of log that this one I don't need, so I just remove it. And let's, okay, yes, Vim, this is Vim. Okay, then I continue. So here I have the ZYNQ PS, and whatever we have said about the ZYNQ PS in lesson 8, they are all inside here. And as you instantiate the ZYNQ PS inside the design, don't forget to run block automation. So the first thing I do, I run block automation. And what does this block automation do? It doesn't do anything special. It just connects the fixed IO and the IOs related to DDR to their respective, in fact, pins on the design. Okay, so just run block automation. And for this block automation, we have an equivalent TCL command. Again, I store this equivalent TCL command. This was the TCL command that instantiated the PS, and this is the TCL command that runs the block automation. And now let's regenerate our layout. It can be more clear. In ZYNQ PS, I have a set of inputs and outputs that I have described in lesson 8 to you, the AXI interfaces. Here we have a set of outputs for timer modules inside the PS. I don't need them at the moment, so we can leave them as they are there, no problem, or we can clear them. One thing which is important is that now the output of the FFT unit should be somehow copied to the DDR memory. So the output of FFT unit should go to an AXI Slave port here somehow, and then it should go to DDR memory. And the point is, the AXI slave ports that we will have here, as I described to you in lesson 8, these are all memory mapped AXI interfaces, and this guy is an AXI Stream interface, and there need to be a kind of conversion between AXI Stream and AXI memory mapped. How do we do that? There's a module, and indeed there are a set of modules which they perform this operation for us. Here I use the AXI DMA. So AXI DMA, AXI not central direct memory access. Central direct memory access is not for now, it is something else. It is only memory mapped. I don't need it. And what I need is AXI direct memory access. And what is AXI video direct memory access? This is very similar to AXI direct memory access, but is dedicated to when you have streams of pixels, streams of, in fact, frames. And maybe in future videos I will describe to you in detail how you use the AXI video direct memory access. For now, what I want to do, I insert the AXI direct memory access into the story. I regenerate the layout. I don't forget to indeed to save the comments related to, okay, so here we have add AXI DMA, and here are the comments. AXI DMA is added. So what I should do, from FFT unit I should go to DMA, and obviously from FFT unit I should go to AXI S2mm port. Okay, S2mm, stream to memory mapped. So from this stream I go to AXI S2mm port, and then here from S2mm port AXI I should go to the ZYNQ PS. And how do I do that? First, I enable the AXI Slave port on the ZYNQ PS. So I double click on the ZYNQ block, and yeah, this is the interface in the Vivado environment that you can fully configure the ZYNQ PS using this interface. And in the PSPL configuration I have HP Slave AXI interfaces. I described to you all of the HP GP ports and their, in fact, their usage. So here what I want to do, I want to send the data to the DRAM through one of these high performance ports. So I open up this part, this section, and I enable the HP0 port, and I press OK. What happens is that the HP0 port will appear as one of the ports in the ZYNQ PS, and now the AXI S2mm, this port, should be connected to HP0 port. Okay. Yeah, it is supposed to be connected to HP0 port, and I don't know why AXI S2mm, it should get connected. It's not getting connected. What I do, I can also use run connection automation. So I select run connection automation, I select the HP0 port, and then it asks me who is the master that you want to connect to this HP0 port, and I want to select S2mm. So I select what I want, I just press OK. Okay, now let's double check what has happened so far here between the AXI DMA and AXI processing system. Yes, indeed, the reason that I was not able to manually connect the AXI DMA to processing system was that for the processing system, the version of AXI interfaces and the used AXI protocol is AXI 3. The components that we have on the PL and we implement on the PL, they are all based on AXI 4 standard. And in any case, even if they were both AXI 3, we always need a kind of interconnect between AXI memory mapped slaves and AXI memory map masters. So this is an AXI memory map to slave, this is an AXI memory map master, and whenever you want to connect these two guys together, you need definitely an AXI interconnect in between. So I was forgetting to instantiate the AXI interconnect, and this was why I was not able to connect these two guys together directly. Now, thanks to run connection automation, the Vivado has instantiated this AXI interconnect in between automatically, and it has made the required connection between S2MM port and the HP0 port. So right now the signal pass from our sample generator to, in fact, the DDR memory in the ZYNQ PS is kind of complete. And what I need to do, I need to configure each of these blocks. I should make sure that the parameters are correct, and I should make additional connections. So let's go ahead and apply also these changes. Okay, first thing that I want to do is that I want to make sure that my TCL script is up to date. So I have this. I have this TCL command. It is enabling the HP0 port. So I add it here. Enable HP0. And then I think this command I don't need, because from what I see it has been trying to, or no, this command also I need, because this is the command that is connecting the AXI data port of the FFT unit to AXI S2MM port of DMA. So this is also an important command and I need it. So, but this is in the connections part. So I add it here. And then finally, the other command that is very important is this automated connection between the AXI DMA and the HP0 port of the ZYNQ device. So I also copy this, and this is an automated connection. So I put it here. Okay, I have put it here. And let's also add some small description. Automated connection between AXI DMA to HP0, and this one was FFT to AXI DMA. Okay, now if my TCL script is correct, if I close the project, let's say close project, I close the project, save project before closing. No, don't save it. I don't save it. Okay to close project. Okay, and now the project is completely closed, and what I do, I save my TCL script. So let's have it saved, and I have more run example. It's called run example. And what I do, I come to the Vivado folder, and I delete everything. RM minus RF Vivado folder is completely clear. So whatever we did from the first of video up to this point I cleared. Only the TCL script is remaining. Now I come back here to the Vivado environment and I have the TCL console here, and inside the TCL console I call my TCL script. So let's say pwd, where am I? I'm here, source is here, inside run example.tcl, enter. Let's see together what happens. Yeah, and so you see what is happening is that whatever I did, the TCL script is now doing automatically. And well, sometimes it may happen that you create your TCL script and you mistype something or you forget something and the TCL script is not working, and you should go and correct your TCL script. Why the TCL script is so important? The point is, as you go ahead through your architecture, you will begin building more and more complex architectures with higher number of blocks, and this view that you have here getting more and more complex with a higher number of wires, higher number of blocks connected to each other. And at one point you see even working with the TCL is easier than working directly here. I mean, what you do is that you usually use the TCL, you build the basic foundation of your architecture, and then from that point, when you had your first TCL, you begin just updating the TCL and seeing what happens in the block diagram instead of updating the block diagram and looking at the TCL. I give you an example. Suppose that I am building a kind of video processing system. What I do usually these video processing systems, they have several video channels. They are not just single channel. So we have several video inputs, kind of processing should be done on each stream, and then the data should be stored somewhere in the DRAM. And what I do usually, I create one video pipeline, and then I create the TCL script, and then for the rest of the video channels I replicate just the commands inside the TCL script, and I change the instance name. And this way I can create kind of complex architectures very easily using the TCL. So the TCL is important. And now I come back to our story here. Let's have a small look at the data FIFO. So we have the data FIFO block here, and I want to configure the data FIFO to be a kind of block which transforms data or moves data from one clock domain to another. Okay, first you may ask me, where are your clock domains? Okay, where does the clock in this system come from? The clock in this system is practically coming from the ZYNQ PS. So if I zoom on the ZYNQ PS, I can see that there is a port, it is called F clock 0, and this F clock 0 is the clock which is driving currently my whole design. And suppose that I want to have two clocks, one clock for my sample generator and another clock for the rest of the design. So I double click here, the ZYNQ PS. The ZYNQ PS configuration environment opens up, and I come to clock configuration. I come to PL fabric clocks, and currently only clock 0 is active and its clock frequency is 50 MHz. What I do, I enable also clock 1, and I set the clock frequency of this one to 200 MHz. Okay, and I press OK. Okay, now here we have an additional clock, which is clock 1, and I can use it for my design. And for the reset, as far as I remember, there can be also a specific reset related to clock 1, but I personally believe that maybe this guy is enough for our task, and we are not doing that special task to have a separate reset for clock 1. So the same reset I intend to use for, in fact, my entire architecture for now. And later, if it didn't work in the real hardware, maybe we decide to have another reset, but I don't think so. So I have the clock 1, and my clock 1 is indeed 200 MHz, and I want to use clock 1 for driving the clock signals of the FFT, of the AXI DMA, and clock 0 I want just to use for the first module. So let's first delete the clock path, what I have right now, and double click on the AXI data FIFO and tell the AXI data FIFO to be an asynchronous FIFO. So asynchronous clocks I set to yes, and from this point on this module will have 2 input clocks, and it transfers data from this clock domain to this clock domain. Another port that I want to enable here is the TLast. The point is, okay, the point is, just let me press OK and I tell you what is the point. The point is, if we look at our module, at our sample generator, if I open up the AXI port that I have here, and this is our design, this is the RTL that we have created, AXI port, what sub ports does it have? It has T data, T strobe, it has TLast, TValid, and TReady. And if you remember from my descriptions in previous sections of videos of this lesson, I said we have packets of data with sample generator. In fact, the sample generator is generating packets of data, and the end of each packet is indicated by TLast. So if I open this AXI Slave Interface, which is related to the FIFO, I can see that it has only TValid, TReady, and TData, but I want the TLast. I want also the TLast to be transferred. So what I do, I double click on my AXI data FIFO, and I tell him I want also to have the TLast. Okay? And then there are other configurations. For example, you can also enable T-strobe, you can enable T-keep, but for now I don't need them. For example, for T-strobe, with T-strobe, I don't remember if I have described before or not. With T-strobe, you can indicate if you are transferring a set of data. For example, you are transferring 4 bytes of data at each clock cycle. With T-strobe, you can practically indicate which of these 4 bytes of data are valid and which are not valid. Okay, but for now, let's assume that in our design, all of the data are valid when they are transferring from one module to another. So for now, I don't want T-strobe, and I want just TLast, and I enable this. And what will practically happen is that the Vivado will connect T data to D data, TLAS to TLAS, T-ready to T-ready, and T-valid to T-valid, and practically this T-strobe will not be connected to anywhere. It's not important for me at the moment. But if you are working on a kind of design that in one data transfer it may happen that some bytes of the data are not valid, then you may like to also consider enabling the T-strobe. So what is happening is that I have the TLAS port here and I have the TLAS port also added here, and then you may get worried about the width of data. For the AXI FIFO, here it's indicating that the width of data is 8 bits, and here the data that I am generating, they are 32 bits. And what is happening? The AXI data FIFO, for the data widths, it has a kind of automated mechanism. Indeed, for the data widths, it looks at the module which is connected to the AXI data FIFO, and then it uses the widths of that module for its own internal widths. But if it didn't happen, and if you wanted to be completely explicit about the widths of the FIFO, then you can also enable this one and indicate the widths of the FIFO. For now, I put the depth of the FIFO just to 512 samples. I really don't need more than that. I believe that the configuration of our AXI Stream FIFO is kind of ready, it's kind of complete, and what I want to do, I want to just connect its clock signals. So as you remember, we have the AXI S clock, which is this one, and it's 50 megahertz, and we have AXI S clock, which is this one, and it's 200 megahertz. So let's connect this one to, I go ahead until I find the PS. The PS, where is the PS? Okay, is here. This one is 200 megahertz. Okay. Well, it will not happen again. And this one is 50 megahertz connected here, and also this clock, which is 50 megahertz, is the clock with which our sample generator is working. So let's also indicate here I have the clock signal, and these two clocks are practically the same. And for the reset, I use the reset that the reset generator module has generated. I think it is fine. So the reset generator module, it has generated one reset for the interconnects and one reset for the peripherals, and at the moment let's have connection between the reset here and the reset in the peripherals, and also here. So I come here, I leave the key of the mouse, then I click, here, here, and every other reset that you want to connect, you can also just click and they will be all connected. Okay, then I continue, clock, also these clocks. Okay, now we want to the FFT, we come to the FFT block, and for the FFT block there are a set of configurations that you can do, number of parallel channels for which you calculate FFT. For example, you have two A2Ds operating in parallel and you have two channels of data entering the FFT. For now it is one for us. Then you have the transform lengths for the FFT module. Just suppose it is 256. And then you have one very important configuration, and that is the clock frequency with which the FFT module is operating, one configuration, and your sampling clock frequency indeed is the sampling rate of your A to D, is the rate at which the sample generator is generating samples for your processing pipeline. So here for our design, this guy is 200 and this guy is 50, and this is important. And then you can go through the rest of the operations of how you want the ZYNQ FFT block to implement for you, in fact, the calculation down in the FFT, what kind of architecture you want it to use, and if in fact what kind of data format is going to be entered to the FFT module, additional ports, and for the memory, should it use the distributed memory or should it use the block memory, and yeah, the output order you want to, in fact, a reverse order for the calculate coefficients, or you want them to be in order, which will increase obviously the amount of hardware that the FFT module will consume. So at the moment I don't want to do any further modification. The only modification that we made, it was here, and this is the FFT module that we have here. But I should make sure that the width of the data is correct, and please be noted that this data, we are assuming that the sample generator is producing valid data for the FFT. This is not the case. When you have a real signal processing pipeline, then you should be careful about the correct arrangement of the bits of samples that enter the FFT unit. For now, it is not important for us. Then we have this AXI Stream Slave Interface, through which you can change the configuration of the FFT block on the fly. And for now, I leave it unconnected. I don't want it. I have just one clock, and I connect this clock to my 200 MHz clock. And then the FFT module creates a set of, in fact, events for you that you can use to control and monitor the operation of FFT unit. Then we have the AXI DMA, and I again double click on the AXI DMA, and I want to change some configurations. First, for now I disable the scatter gather engine. What is the scatter gather engine? Is a kind of mechanism that the AXI DMA can use, or in fact you can use as the designer, which allows the AXI DMA to perform data transfers without disturbing the CPU at all. Indeed, if I disable this mode, what happens is that every time that the DMA engine performs one data transfer task, it should interrupt the CPU, and CPU should reprogram the DMA engine for the next transfer task. For example, if the CPU configures the DMA engine to transfer 1 MB of data, after this task is done, an interrupt will be generated by the DMA engine to the CPU, and the CPU should come again and reconfigure the DMA engine for the next transfer task so that the next data transfer can begin. In many of the applications, that is okay. It doesn't drop the performance of the CPU really, since the interrupt rate is small. But if you enable the scatter gather engine in the beginning of DMA operation, you in fact create kind of linked list which describes from which location to which location and what amount of data each time the DMA engine should transfer. In fact, you define the set of transfer tasks for the DMA engine and you put them somewhere in the memory, and as the DMA engine accomplishes one transfer task, it automatically proceeds to the next transfer task and then so on. And it doesn't disturb the CPU at all. The scatter gather capability is very important, especially when you have complicated data transfer tasks. We will talk about this in more detail in future videos. For now, I disable this capability. Furthermore, each DMA engine or AXI DMA engine or AXI video DMA that you instantiate in the PL has by default two channels. One read channel from which it reads from the DRAM or from the memory mapped interface and puts the data on the stream interface, and one write channel by which it receives the data from the stream interface and puts the data on the memory mapped interface on the DRAM. For now, what I want to do is that I want to transfer data from the stream interface to the memory mapped interface and not the reverse direction. So at the moment, I just disable the read channel and just keep the write channel active. And here in the write channel, I have the burst lengths that I can configure. And this is the maximum burst lengths of the transactions that you allow DMA to perform. The higher the number of burst transactions, the higher will be your total bandwidth, and the change in the bandwidth can be significant. So it can be really clear the bandwidth that you have when max burst size is 16 compared to the bandwidth that you have when max burst size is 256. It can be a huge change. But as you go toward higher burst sizes, then you may block the system, or you may block the hardware that you have on the PS and are responsible for transferring data to the DRAM for a larger amount of time. In fact, with larger burst sizes, you are keeping or reserving that hardware for a larger amount of time for this module, and the rest of the modules on the hardware cannot access that specific resource, the memory, at that time that the burst is being done. So you should look at the application that you have and the priority of these data, and the priority and the importance of correctly transferring this data to the DRAM. And based on that, you should select the burst size. If the rate of the data is not that high, then you don't really need to select a large burst size. And even a normal burst size is completely enough for your task. However, for example, if you need to transfer 1500 megabytes per second of data to the DRAM, then definitely a burst size of 16 may not be, or the burst size of 16 is not enough for doing this kind of transfer with this high bandwidth. And at that time, you may like to go to the highest possible burst size that you can have. Okay, so this is something that you decide based on your application. Anyway, I keep it at 16 and I press OK. So this is right now our DMA engine. Our DMA engine also has one very important port here, is called AXI Lite, and this is practically a slave memory mapped AXI interface. So this one is a memory mapped AXI slave interface, and this is indeed the port through which your PS, the ARM host that you have here, can program this DMA engine. Indeed, whenever the DMA engine wants to perform a transfer of data between this AXI stream to AXI memory map, the CPU should first program the DMA engine and should tell the DMA engine at which address on the DRAM the data should be copied and what is the amount of data that should be copied to that specific address. So the CPU that we have here, the ARM host, should have a kind of mechanism through which it can program the DMA engine, and the mechanism is this AXI memory mapped slave interface. So I need to connect it to one of the AXI memory mapped master interfaces of the PS, and for this the best option is AXI GP0. Okay, so what I do, this port. So what I do, I come here, run connection automation, and for this port I want to connect it to an AXI master. Xilinx Vivado recognizes this automatically. It says there is one AXI master to which you can connect this AXI slave, and that AXI master is AXI GP0. Do you want to make the connection? You just press OK, and then the Vivado goes through all of the rest of the connections necessary. Okay. So what has happened practically right now? We have now the GP0 port that goes to an AXI interconnect, and then from the AXI interconnect we have a connection to this AXI Lite interface of the DMA engine, and this is exactly the connection that we were seeking for. And now if I look at the address editor, if I open the processing system 7 tab, I can see that for the processing system 7 there is now one AXI slave port, there is now one AXI slave component, and this AXI slave is located at this address. So whenever any of the ARM hosts wants to configure the AXI DMA that we have on the PL, the ARM host should write to this address. In fact, this is the base address on which the AXI DMA module resides, and the ARM host, they should use this address so that they can access the internal registers of AXI DMA module and configure the AXI DMA module with the desired transfer task. Now I come back here, and what I want to do, I want just to make sure that our clock signals are correct. As you can see, the clock is not really correct, and in fact the automated connection system, it has used clock 0 for doing these connections here. Probably or I would say is better to disconnect this net from clock 0 and make it connected to clock 1, so that we can be sure that this part of the hardware is running at 200 megahertz. Okay, this is our design up to this point. I regenerate the layout. It's now kind of clear. We have the ZYNQ PS, We have one AXI interconnect on the HP port, another AXI interconnect on the GP port, and then we have in fact our components connected as we were looking for. Now what I want to do in the next step is I want to simulate the operation of the sample generator, the AXI data FIFO, and the FFT module. I want to see if my sample generator is working correctly or not. So I want to create a kind of test bench for my design, and with the test bench I want to stress this module and to see if it's working properly or not, if the data will pass in fact correctly from this module to this module and then to FFT. So I go in the next section of the video, I update the hardware, I remove all of these blocks, I just keep these three and I remove all of the rest, and for this block I create a test bench and we together perform the simulation on the logic, and we make sure that the waveforms are correct and this module is operating correctly. Before that I have to go through complete modification of the RTL of this module, and then we can do our simulation. Okay, I think I had an overview on how you can create this pipeline, and I want to just have my final note. These videos are hobby, they are my personal hobby, they are not official, they may have mistakes. The goal is, in fact, I want you to learn designing with the ZYNQ device in a shorter time, and I think these videos can help. I would like to thank Professor Norbert Wayne of TU Kaiserslautern and Professor Luca Benini of ETH Zurich because of their support. And you can always find the latest material related to my ZYNQ training videos on green-electrons.com and googlia.com, which are my personal websites. Thanks for watching this video. See you in the next video.